Yes, yesterday we talked about correlation. So before we quickly move to regression now, I want us to, I think we discussed some things about Dr. Kobo raised an issue that the data we use is on the ordinary data, and ordinary data. They have a data set. So I've not shared with you. I've just.
Can I just? Hello, sir.
Yes, go on.
I just want to see that slide that shows by serial and points. I just want to look at something. Sorry.
So okay, look at it, and this is slide.
Points by serial by point by serial by serial. Okay.
Yes.
Okay,
So,
now I understand. Okay.
Yes.
By serial,
I have a data set here. I'll just quickly share so that you see. I explain how this is being done. The third candle and possibly the other one, which is the sperma with the same data set, and we'll quickly run it so that we won't waste much time on that. So let me just share what I have here with us. Okay. No, it's not this one. Director, okay. I think it should be this one. Dr. Larry, welcome. Dr. Larry, you saw the video I sent to you, right? Welcome. Yes. You saw the. Were you able to open it?
Okay, I will check.
You have been watching it. Oh, you didn't watch it. You didn't open it.
I think I've been busy since morning.
Okay. No problem. I just want to. Okay. Yeah. Yes, there's a data test here. What you have here, can you see? I'm sharing with you. What do I call it? I'm sharing with you an SPSS data. Can we see it?
Yes.
So it's a ranking. There are 12 people. Maybe they came for interview, and the director, the first rank, the director ranked them according to their performance, and the other one, manager ranked them. So you can see now, the first rank is that of the director. He arranged them according to his own rank, from first to the last. So that subject is just a number. I just give it number. It doesn't really matter. That one can be helped. It means I just number it better. This is the rank. The director arranged them from the first to the number 12
to the 12th.
To the 12th. While if you now put the manager's own by the side, the manager rank, the one the director says 2, number 2, manager says 1. So a rank is own. Can you see? So this is the type of thing you use Kendo and to really correlate the two ranking. Now we can actually calculate both Kendo and sperma out from here. So like now, the logic behind the Kendo, we have already talked about sperma yesterday. The logic behind the Kendo is just to look at what they call concorder and discorder. Yes. Concorder and discorder. And it's a little bit tricky, but we'll not waste more time on it. What they call concorder is that if you look at these two scores as you are going and like if you look at it now, you are comparing the second rank to the first one. What we usually do is so first of all arrange the first ranking according to the rank and now put the other one. So the first ranking will appear according to the rank of that first ranker, while the other one will now be put beside. So now you will now be comparing. We want to start with concordance. When you start with concordance, you see the way it works. When you start with the concordance, you see the way it works. Like the concordance, don't make noise here. So you start with the concordance. So what we want to do now is that I don't want to waste time. I want us to look at these two now, that first person. You want to see for the concordance, how many of this opposite one Why is this thing freezing? Just a minute. Let me reshare. Yeah. How many of these opposite one, that is of the first one, that's below this first one, how many of them are more than the first rank? So anyone that is among the first rank, and you are using second rank now, let me hold this now. Among this the second rank, the first rank, how many are greater than?
You can come back tomorrow or till you're ready to start.
How many of these? So if I want to use the notation to write, I don't know why that thing is not coming out. I want the writing. Yeah. So this one now, how many are for this first rank? Now, if you are looking at this number, the first for this rank 2, how many of these first rank are more than these two? Can you see now? Those are the concordants. So if you look at it from here down, because there are 12 of them, 10 of them are more than these two. This one is not normal. So the concordance and the role of the concordant is 10 that is there. Then for this one, for this second one, how many below are more? If you look at it also, you can't. You can't. If this one is no, is it 10 or yes, it's 10. If you look at it, for this first one is 10 because 1 and 2 are not part of it because 2 is the same, it's not below these two. So if you count from here down, there are 10. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. That's why it's 10 here. So these two, how many are less? It's 10 also from 3 down. All of them are still greater than this one. So the concordance there is 10. Then for this one, how many are below 4? If you look at it from 5 down, 1, 2, 3, 4, 5, 6, 7, 8. There are 8.
This one is
For the 3, for this one, how many are less? Is 8 also. 5. Yeah. If you count it, there are 8 of them that are greater than 3. For this one, how many are greater than 6? There are 6 of them because 6 is not greater than 6. So from 7, 8, 9, if you count it, there are 6 of them that are greater than that value. Then for this one, how many is 6 of them also from that 7 down? For this one also, how many? 8. How many? This 8. How many are greater than 8 here? 8 is not greater than 8. So 8 is out of it.
Okay, another mirror.
There are 4.
Okay.
4 of them. How many are greater than 7? I don't want, please, people should not make noise. Mute yourself if you are talking from your hand. So this one, how many are greater? Is 4 also, from 7 down. Yes, this one, how many are greater than this 10? There are 2. 10 is not greater, so 11 and 12. This one, how many is 2 also?
I'm not getting this thing at
Here
all.
is 0. There's no.
It is now the onus is on you because at the end of September,
I don't know. I don't know. Some people are making noise. I don't know. You say you don't get it. People are making noise from your head here. People are making noise from your head.
Specific for Hala. So if you identify all those things, payments that have not been made,
It's actually not me.
individual or vendor, write to Chibuzo. Or you can ask.
I want to know is
Chibuzo directly.
is Oyinlo, is Jane.
It's bad. It's not.
All those things I've written, I will go because it's not a permanent something. I didn't save it. So you say you were not getting. Who was not getting what I was doing? I just want us to quickly do that. The only day I can do something will go. Who was not getting what I was doing? But nobody answer again.
So I was the one. So I was the one. Hello?
Hey, me, I understood everything.
Okay.
Can you hear me? I didn't understand it too.
Let me repeat it. Let me repeat. Let me just repeat it. Let me just repeat.
Slowly, please. Okay.
What do you say? Let me just repeat what we have just done. It's only that I thought maybe I will just put on a table. If I put on a table and just explain, I just thought maybe something you just get to understand quickly. But no problem. What I will do, let me just go to the slide and put it there. No, I was actually in that. Okay. Let me just put a table here. Let me just put a table before we go and solve it, because it's very, very important. We didn't get it. I think that.
Yes, sir. Thank you, sir.
Yeah. Okay. 4. So what I was just doing is rank 1, the first ranker, director's rank, rank 2, and concordant, discordant. Okay, it doesn't want this discordant. Yeah. So you know the rank are 12. Actually, we'll see, try to sum it. Please. So the other one, the way the rank was like this. Yeah, this is the way the rank. Can everybody see? Everybody is seeing, right?
It's only the new one we are doing. We can't see that one.
You can see the
It's
new
the
one
old
you
one
were
that
doing,
is there.
the old one.
No, I'm coming. Don't worry. I will share. Can you see? Can you see? Can you see what I share?
Yes.
You can see?
Yes.
Because I'm typing.
Yes.
Yes, sir. Yes, sir.
So now what we want to do is these are the two we want to see, calculate discordant and concordant. That's all we need. The formula is just very simple. They're just like a McNema something. That's just the way the formula works. Though there is variation, but that's the common, because this candle you see, there are candle tau A, tau B, and tau C. So there are different variations, but the one that is being used, you see in any statistical package, is tau B, and this is what we want to calculate now. Now, the concordant just means that if you look at, you first of all arrange the first rank from smallest to the highest, but you now put the second rank beside it. Yes or no? So you put it there. So you now pick this second rank now. How many of these first rank that are below the line as you are going down? You know, you are following this rank, the ranking of the first one. From the second one, I want to know how many of these first one are that are below this first rank. When you say below, you know, that is after this first one for that second rank now, after this first row, the first person for that second rank, how many are greater? Here. So here now, you know that 2, 1, 2, okay, even 1 is not even below it. These 2 is the same value as this one, so it's not greater. So the one that are greater start from 3. If you count it, 3, 4, 5, if you count them now, there are 10 of them. You know there are 12. If you remove these first 2, this from 3 down, there are 12. There are 10 rather. So the component, the number that are greater than, there are 10 of them. When you come to this level now, this one, how many are greater from this side, from below, from this side? Is this 10 also? Do you get that one now? Before I proceed, do you get what I just did?
I thought it to be 11.
How can it be 11? Because if you look at it, this 10, we are here now. We are in this 10, in this number 1. This one, they put 1. We are considering the row below, or the row below it. So how many on this side, this first rank, are greater in value than this first one? If you count from 3 down, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. There are 10 now. Did you get what we are saying?
Yes.
You should answer me now.
Still not getting
Yes.
Okay, let me do the next one. Maybe you get it. Look at this 4 now. We are want to do for this 4 now. So from a line below the 4, which is from here,
Yes.
how many have value greater than that 4? Is 4 is the same value, so it's going to be from 5. 1, 2, 3, 4, 5, 6, 7, 8. There are 8 of them. Because 4 is not cannot be part of this 4 is only part of because it's not greater than this 4. So
Okay.
so it's from if you count from here now down, there are 8 of them.
Okay.
So
okay,
for
I get
this
that
3
one.
now, for this is the same thing. For this 3 now, if you come from below now, from this down, there are 8 of them also. If you count 1, 2, 3, 4, 5, 6, 7, 8, 8 of them. You are confused. They are having the same value. Why they are having the same value? For this one, there is a 4 here, which is not below that 4. That's why you cannot count it. That's why it gives you 8. But when you come to this 3, all of them below, they are greater than this 3. That's why it's 8. So when you come to this 6 now, how many are below, are greater? 6 is not part because 6 now is the same value. You're going to start from
7, Abby.
7, 8. So that would be 6 of them. So you put 6. So for these 5 now, how many are more? Is 6 of them also from that 7 down, 6 of them. Then from for 8 now, how many are more? 8 is not part of, so you count now is 4, 9, 10, 11, 12, 4 of them. So this one, how many are more? Is 4 of them also. Sorry. It's 4 of them also. Then this one, how many are more than 10 there? Is 2 of them. This one, how many are more than 9? That is 11 and 12, 2. Here, how many are more than 12? It's only this 12 that is here, and it's the same value, so it's 0. You cannot do, there's nothing below 11. You understand me now? So you cannot do.
So is it that rank 2 that you're using to do all this concord? Because I know you were saying how many are below this.
Yes, below the value of rank, the second rank. You are looking at the opposite side. You are using the second rank. You are looking at the value of the second rank. You now look at the opposite side. How many value are more than that value on the opposite side? Can you follow me?
Yes, sir. Yes, sir.
So we have just done the concorder now. You are looking at how many are more. In this quarter, how many are less or equal to? Can you see just the opposite? So when you come here now, how many are less or equal to? So if you look at it 2 now, from below, how many are less or equal to? It's only these 2 that is equal to. Can you see? Can you see?
Yes.
Among the, so it's only one of them, which is that 2. So when you now come to this one, how many are less or equal to here? There's nothing less or equal to 1 there, so it's 0.
So you're fast too. You're very fast.
Okay. So what's the? Is it too fast?
Okay, the first one, is it discordant?
The first one is concordant. This one I'm doing discordant now. Look at discordant now. The second row now discordant. For the first one, I say these 2. When you consider all the value below here, how many are equal to or less than that 2? How many? Answer me now. Is it there? Ugo. Okay, let me just continue. Don't. Okay.
No, sir. I'm here, sir.
But I said you should answer me. I said, look
sir?
at this one, these two.
Yes,
these 2
yes.
as a value. When you look at the opposite, this opposite side down.
It's only 1.
Yeah, it's only that 2.
That is not.
Yeah, that's why I put 1 there. That is.
Oh, I now understand. Okay,
So
okay.
when you come to this
the
level
opposite
now,
side.
Yeah, this one, how many are less than 1? When you come to the second one now, there's none is less or equal to 1. Can you see?
Okay, I get it now.
That will be 0. That's why it's 0.
Hello?
So when you come to 4 now, how many are less or equal to 4? It's only the 4. Can you see? It's only the 4. You put 1 here. Then
When it comes to 4,
yes, now how many? On the opposite side.
that is the opposite side.
Yes, now how many of them are less than or equal to 4?
Okay, equal to. Okay. I don't understand. Okay,
it's only 1.
Equal to.
Yes. So when you now come to 3 now, how many are less than or equal to? There's none. It's 0 also. Yeah. Then when you come to 6, how many are less than or equal to? It's only 1. That's 6. 1. Then when you come to this 5, how many are less or equal to? There's none. When you come to this 8, how many are less or equal to? Is that 8, which is 1. Then when you come to this 7, how many are less or equal to? There's none. 0. When you come to this 10, how many are less or equal to? Is 10 itself, which is 1. So when you come to this now, how many are less or equal to? None. When you come to this 12, how many? What do you say?
No, I'm not understanding it. Yes. Then when
this 12, how many are less or equal to? It's just only this 1. So like this.
Oh, okay.
So when you now add, let's sum all the discordant and concordant. When you sum the discordant, this is 20 plus this and this, 28 plus this, 36 plus this, 42 plus this, 48 plus this, 52 plus this, 56 plus this, 58 plus this, 60. So the total sum for concordant is 60. And when you add this one, 1, 2, 3, 4, 5, 6, is 6. The discordant is 6. Are we following now? Are we together? So the statistic you are calculating is the candle tau B you are calculating. Coefficient you are calculating is equal to C minus D divided by C plus D. Can you see now? So divided. Can you see now? The C is the concordance, right? So what is telling you the answer now is, let us say, is equal to 60 minus 6 over 60 plus 6. Are we following? Which give us 66 divided by, no, I think 66, 54 rather, divided by 66. So if you calculate it, what does it give you? What does it give? Somebody should calculate it for us. Which is 0.818. So the
0.818181818.
yes, just wait 1 just leave it as 818. That is the Kendall correlation. Is it clear now? So let's run it, you will see. And if, let's say, we want to do for the same thing, if you want, let's say we even want to do for, let's say you want to do for, what do I call it? The same thing. You may decide to say you want to calculate for, let's say you want to calculate, let's calculate for sperma also. No, we can calculate it for sperm. We can use it for sperma also. We want to use the same data set for sperma. What we have just done now. You remember the way we calculated sperma? You know, we calculate D, the difference, and D square. I think you remember yesterday. Are we following? Please, I want us to respond.
Yes, sir. Yes, sir. Yeah, I
Yes,
totally
sir.
agree. It's different.
Yes, sir.
Yeah, D.
I remember that formula.
And let me just look at it. It's got to what? D squared. That's what we want to calculate because every other thing is constant. The sample size, n squared, all those things. So if you want to calculate for Spearman now, all you need to, okay, what is the difference between the ranking? That's all you are looking for, the two ranking. If you look at it, one thing you can even forget about the sign because the sign has no meaning. Yes, I mean, because either it's positive or negative, by the time you square the D, it cancels out the sign. But you'll be surprised, look at it. What is the difference between first and second? It's 1. This one, 1. This one, 1. If it appears everything is 1 here, it's there between the two ranking. Do you follow? And if you square 1,
So wait. I thought so. I thought it's supposed to be different.
difference as how? Yes,
Rank 1 and rank 2.
Yes, do the difference now. Okay, let's remove rank 1 from rank 2.
Sorry, I've seen it.
So
I've seen it.
what this
Okay,
will
yeah.
give you minus.
Yeah,
Let's
correct,
remove
sir. Yeah, correct.
1 from rank 2. Let's remove rank 1 from rank 2. Let's say we remove
That's
1.
minus. So
So
is it rank 1? Is it rank 1 from rank 2, Abi? Okay, so that's
yeah, 1 from rank
1 minus 1 1 minus 1 1 minus 1. Okay, I get it. Don't worry, sir.
You get it
Thank
now?
you. Yes, sir.
Yes. But if you square them, it becomes the same one. You understand me now? If you add it together, this one will be 12. Is it not 12? This square will be 12. If you feed it into the formula we have here, it's going to be 1 minus, if we are to calculate it now, want to calculate it for, this is, I'm coming, this candle. We want to calculate for Spearman now. Spearman. Row. This one is only row. Because now is equal to the Spearman will be 1 minus 6 sigma addition of D square so you come down here. No. So over n into n square minus 1. This is the formula. This is formula for the so if you are to do it now, row. So if you are to do it now, it's going to be 6, you go to 1 minus 6 times 12. It's not 12 we got for that one. Are we together? Please be telling me. This one n.
Yes, sir. Yes,
12,
sir.
which is 12, right? 12 times 144. Because 12 times 12 is 144 minus 1.
Wait, sir.
Yes. The sample size is n.
Okay.
The n is 1. Is
The D squared was 12.
this square was 12. Yes, now it was 12.
Okay.
The addition is
So
12.
that will be 1 minus, wait, let me see. 6 times 12.
Yeah. So when you now do it now, so somebody 6 times 12. Actually, you can even cut. You can even divide this one because 6 has already cut 6 here. Yes, I'm now. So it will now be something like.
Minus
So it's good to do the mathematics so that you know the logic behind it before you go and be solving. So this one will be something like 6 times 12.
71 divided by.
You can just say 12 times 143. Do this one. If you remove this, it's 143. So all you need to do, yes, now because
how you get
144 minus 1.
Oh, I see what you did. Okay. Because what I did was I multiplied 12 by 144. Multiplied 12 by my minus 1.
You will see. You are wasting time on that one now. If you have to do, you have to multiply 12 by this one and remove it. So
yes, I'll remove it. That's what I did.
Why not just do it like this? Or if you even divide this 12 by
right,
this, it's going to be 6
and
over
it gave me the
143.
same answer, safe.
6 over 143. Then remove it from 1. That will be the answer. Can do that. 6 over 143. Then remove from 1.
0.04. So what did you say?
It's going to be 6.
To do what?
6 over, I'm trying to do 143.
That thought is 6 times. Please, I thought it would be 6 times 12 divided by. Will it not be 6 times 12 divided by 12 times 143?
But why are you wasting more time? The answer is 0.5.
So I want to learn it.
Yes, you learn it. That's what I'm doing. What I did now, 12 cut 12. Instead of you multiplying, 12 divides cancel 12 now. You have finished. You have forgotten your board mass.
Oh, that is true. Oh my goodness.
12 cut 12. 6 divided by 143.
Yes, 0.06.
So if you remove it from 1, it will give you this.
0.1 minus 0.0419.
No other person is talking here. Is it that we are not following?
0.0.
Are we all together, please?
So the answer is 0.9851.
0.95.
Wait.
No.
Let me do it again. This doesn't make any. With 6 divided by 143. That's 0.0419.
So the answer is 0.958, yeah?
0.0.
So there's no. Are we following? Is it clear to everybody?
0.4195.
Yes, sir.
So the answer I'm getting is 0.958. Oh, sorry.
And yes, now 0.958. That's the answer. That's the answer I put here now.
Oh, sorry.
That's the answer. Is it clear?
Yes, sir. Thank you, sir.
So the Spearman correlation is 0.958 for the same data, and the Kendall is 0.818. One thing, the Kendall is usually lower than the Spearman for a particular data set. Both of them are for rank correlation. But people prefer the Kendall whenever the sample size is very small and there are a lot of tie rank. Okay, let's quickly run it now. You know, I will share the data with you, but because I have it, let me just run it so that I just go straight to this business. So, you know, how to assess correlation is very simple. Just say, okay, let me share. It's like, have I share? Can you see the data set? Can everybody see this data set? Please, I want us to respond, please.
Yes, sir.
Yes, sir. Yes, sir. Yes, sir.
Yes.
So analyze, correlate, bivariate. That's it. Yeah, yes.
So let me show you to select Kendall, Abi.
Yeah, I've got look at it. Yes, I know I've run it before. Look at it. Normally, it will give you something like this. It's person that will be by default. Select Kendall.
Oh, I see.
Tema, just click.
Why are you selecting all of them? Okay, you want to do it at the same time.
Yeah. If you look at it, usually run look at the correct spacing. 0.9.
Please share your screen again.
Yes. Oh, I have not shared. Sorry, let me share the output. So you're welcome, Dr. Udusholu, Dr. Larry, Dr. Emmanuel Kagu, Dr. Jane. You're welcome. Okay.
Good evening, sir.
Yeah.
Good evening, sir. Thank you, sir.
Good evening. Yeah. So, can you see now? Can you see it? Can you see the output? Please, I want people to respond, please.
Yes, sir. Yes, sir.
we can see it. We can see it.
Yes.
You see, can you see now the non-parametric? Can you see the candle tau? Candle tau. Can you see 0.81?
Yes, sir.
You know what you got?
Yes.
Yes, sir. That's what we got.
And that was what you got. Yes, 0. And if you look at the other one, come down. Spearman 0.958. That was what we got also.
Yes, sir.
Yes. It happened
That
also
formula
that,
was okay.
What is it?
That formula was it C minus D over C plus D?
Yes. This
Okay.
C minus D over C. You know, if you remember, that's the logic behind the what do I call it? McNema. You remember? The difference
Yes.
between this discorder over the difference between the discorder over the addition of the discorder. But this one is the difference between the concorder and discorder and over addition of the concorder and discorder. Yes, I mean now. So if you look at it, when you say the difference between two things over the addition of two things, that shows that the numerator can never be greater than the denominator. Yes, I mean now. But it can be the same, because if the figures are maybe, let's say 60 and 0, so the difference between them and addition, they will be the same thing. So 60 plus 0 over 60 minus 0 over 60 plus 0. If you use 60 over 60, it will be 1. 1 over 1 will be 1. That's why correlation cannot be greater than 1. But that numerator can never be greater than denominator. If you get it now, it will be less or equal to the denominator. That's why it will be 0 point something. I don't know if you get the logic now. So I think we proceed. We proceed to
regression.
Yeah. So actually, if it just for you to know the logic, if you, in real life now, all you need to know is to know the reason you should use any of them, and just use the SPSS to run it. So actually nobody want to be calculating. Even sometimes
manual.
Even sometimes most time, even when you are even doing MPH, hardly with somebody ask you, they may ask you for other things, but to be calculating in that type of thing in exam, sometimes it's not something that is straightforward. Because sometimes for you to quickly generate some of those, you may have to use like for correlation, for it to take time. For correlation now, it's easy. You can use Excel to just generate those square minus this or those stuff. So it's just for the essence of this, for you to know the logic, some formula behind it. Then you just know how to use the machine to run the analysis.
To do it.
Yes. So let's go to regression.
So I hope you will send us this data.
Yeah, I will send this one. I will send it.
Okay, thank you.
I will send this last one here. You know, I've sent everything except this one. I will send it. I will send it. Okay, let's quickly look at regression. The term regression, you know, as I was telling you, we have been discussing this regression for so long. We have, I'll be telling you that regression and ANOVA is the same. And if you were excited yesterday, that yesterday's one will be small compared with the excitement of today, because there are some things behind this regression. You discover that these statistics, when we talk about linear modeling, whatever, removing confounder, statistical modeling, that is the basis. And nobody can draw any conclusion, valid conclusion, in any study, especially if you want to know the factors responsible for something without doing multiple regression. It's not possible. Because if you just go and do literature review and can pack your study with a lot of factor, which is okay, and you just do ordinary bivariate analysis, you just identify amount of passive factors, say this one. You don't even know the reason for each of them because some of them don't make meaning until when you now run multiple regression, you'll be able to know that some of them is because of confounder. And it's this regression that brings out the solution. The term regression is a historical anomaly. It simply means that the average value of y is a function of x. That is, it changes with x. Let's just quickly look at some historical background. The earliest form of regression was the method of least square. We're going to talk about this method of least square. This was.
Sir, are you going to? Sorry,
Are you not seeing what I'm showing?
No, I want to check. I didn't understand that.
Have we done anything yet?
Thank you.
This is
You didn't understand
bored.
what?
Hey, I just wanted to see that first slide.
It was shown now.
Okay.
So the thing is
It
getting
was shown.
bored.
You are making some prof impatient here because some of those you just take your question so you can ask later. So what do you want to see here? It's just an introduction, and I still share with you.
Thank you, sir.
After the workshop, I'll still share this slide. So the earliest form of regression was the method of least square. This was published by Legendary in 1805. Can you see when? And by Gus in 1809. The phenomenon was that the height of descendant of tall ancestor tend to regress down towards a normal average. The phenomenon was referred to as regression towards the mean. You know, it has to do with how this regression of a thing came out. It has to do with height of children and their fathers, ancestors. The word regression sounds like go back in some ways. The term was has appeared in early writings since the late 30s, even before that man published that work. Since late 30s, 30 something, and it derived from the Latin term regressus, which means a return. That's where a return. That's how the word regression came. It is used in different fields with different meaning, but in any case, it is always referred to as action of regressing. Now, in philosophy, regression is used to indicate the inverse logical procedure with respect to that of the normal apodictic. I try to find the meaning of this thing because it's another word they put there, apodixis. You know? Apodixis means demonstrable or indisputable truth. You know, those are,
philosophical.
Yes. What they were using those days. But the meaning is demonstrable or indisputable truth, in which it proceeds from general to particular. But you get, whereas in reality, in regression, we go back from the particular to general. That is from effect to cause, or from condition to condition. I don't know if you understand that. If you look at it, as we go to see later, you are regressing the outcome on the exposure. Can you see now? If you look at, you put Y. You want to know what are these factors. You know when you are studying a phenomenon now. You say you are studying your in research. Your outcome measure is your research question. If let's say you are interested in what are we are talking about, maybe anemia, or let's say hemoglobin concentration, low hemoglobin, either low or high. So what are the factors that are responsible for hemoglobin concentration or PCV or whatever? So you look at your outcome measure is hemoglobin concentration. It's going to be the Y. You now look at the factors. So when you analyze, you are starting from the value of hemoglobin concentration to actually know what are those things that cause hemoglobin concentration. That is regression. That is, you are from effect. Effect is the hemoglobin concentration. Those things that cause it are there are a lot of things you want to trash out. Which of them is the most important? So that when we want to recommend, we give recommendation, we solve the problem of hemoglobin, of anemia. I don't know if you understand this thing because
Yeah.
that's part of the answer. That's what it's saying. So regression is actually you are moving from effect to cause. Of course, normal progression is that something cause an effect. So we have already seen the effect. Now I want to trace back what is causing this problem. Just like whenever we have problem, we want to trace back what are the cause of this problem. Of course, the cause of this problem came before the problem, but we didn't know them. But when we have seen the problem now, oh, this is a problem. Oh, let's begin to trace our step back to see what caused the problem, so that we can go and stop that type of thing in the society, so that it will not, cause it more for the in the future. You're like somebody that is already have diabetes already. You are just trying to reduce complication. If somebody that already have complication of diabetic or hypertension already gotten it, all the study we are doing, well, we may want to know how to help the people, but more to help the people that are coming that have not get it, so that these are the things that these people did that make them to have complication or have diabetic or whatever. Don't do it so that you don't go. So in regression, what it does anyway, it's not really regression. Research is about that. So that is why you now know that the regression is the meat. So come from condition to the condition. Now, in statistics, the term regression has an ancient origin and a very special meaning. The man who coined this term was certain Francois Gattin. He was a geneticist. I've already told you that most of the people that developed statistics were biologists, were genetics, were biologists, and then some social scientists also, because they needed the statistics more. So the statistics were not developed by mathematician. Though it's a branch of mathematics, but it was not. You will see that they borrow a lot of things from mathematics. Yes, but the people that developed were not mathematicians. They were biologists and social scientists that actually needed this thing. There are a lot of variability in genetics. Genetics, study variation. So that is why they needed statistics. So in 1889, this man, Francis Gattin, published an article in which he demonstrated how every characteristic of an individual is inherited by their offspring, but on an average to a lesser degree. So, for example, children with tall parents are also tall, but on an average, their height will be comparatively less than that of their parents. And you're going to see also, children with short parents will be short, but their height also will be higher than that of their parents. Can you see? Average for their parents. I don't know if you are following me. Now, this phenomenon also graphically represents, okay, it's called regression. So they can represent by graph. We're going to show how the graphs come. Since then, this term has lived on to define statistical techniques that analyze relationship between two or more variables. Can you see how the origin of regression? In Gattin's work is correspondent. This corresponded to the concept of regression towards mediocrity. That's what I mean. Regression towards mediocrity. What this one means that, for example, if you see parents that are extremely very tall, maybe both mother and father, whatever, or even maybe one of them, you see parents that are very tall, their children will be tall, but they will be average, they will be shorter. Thank you. They cannot be because they are beginning to be tall like a pole. They will come down. They will be shorter. Though they will be averagely taller, but they will be shorter. When you also see children of short parents, they will be short also, but they will be taller than their parents. So the issue is that somehow, if somebody is similarly tall and similarly short, the offspring will try to come back to the average, which is not too short, not too tall. That is regression to me, where they call it mediocrity, but to me it's regression towards normal. That's the way I put it. Now, Gattin universal regression law was confirmed by Carl Pearson. Capesi was guiding students. Capesi was the first to describe Pearson correlation we discussed yesterday. He was the first to discuss chi-square. So he was first to describe correlation, first to describe chi-square. That's why you have Pearson chi-square. And he was regarded as the father of mathematical statistics. So to me, maybe after Fisher in statistics should be Pearson.
Pearson.
Because yes, after Fisher. I think Fisher was the one that contributed most to statistics. And Fisher also was a genetist. He collected more than 1,000, that is Pearson, collected more than 1,000 height of member of family group. He found that average height of children from a group of short parents was greater than the average height of their father's group. Average height of the children from a group of tall father was lower than the average height of their parent group. That is, the height of all tall and short children were regressing towards average height of all people. And you see, so if their parents go to the extreme, they try to come back. Now, let's now talk about regression. It's a way of predicting an outcome variable from one predictor variable or several predictor variables. Can we say we have already said under the historical background that regression is you are moving from effect to cause, from conditioned to the condition. That is, somebody that thing that was conditioned, what conditioned it is the condition. So from effect to cause. So that is why it's a way you are predicting outcome variable from one predictor, that is, if it is one predictor, that is simple regression. In that case, you are dealing with your outcome variable, which is one variable, and one predictor. How would that one predictor affect it? That is simple regression. Now, if you include at the same time, concurrently, you try to see the effect of more than one predictor, that is 2, 3 or more, that is multiple regression. And that is the multivariable analysis. And we're going to talk about, you know, some people call it multivariate analysis. It's misnomer because if you read standard statistics textbook, not sure one, you're going to see that multiple regression, they are multivariable analysis. They are not multivariate analysis. Those that are multivariate analysis, they have more than one outcome at the same time. But regression, multiple, always have one outcome at the same time you are predicting one outcome. So either linear or logistic regression, when you have only one outcome, but you can have one predictor, that's simple regression, or many predictors, multiple regression. And that one with many predictors, which is multiple regression, that's called multivariable analysis, which some people mistakenly call multivariate analysis. It's not multivariate analysis. They are type of analysis that you have more than one outcome and more than one predictor. Like maneuver, multivariate analysis of variance. It's a multivariate analysis. We have multi-dimensional scaling, factor analysis. Those are multivariate analysis. Like now, you can use maneuver to predict at the same time systolic and diastolic blood pressure from the predictor. Can you see? In that case, you will be, since the blood pressure occurs as two, either systolic and diastolic, you can feed in at the same time to predict the value of systolic and diastolic from many predictors. That would be multivariate analysis. And you can use multivariate analysis of variance to do that. But the regression, regression can only predict either systolic alone at the same time or diastolic alone at the same time. So what many people will now do is that's why clinicians use logistic more than linear regression, because in that case they can as well measure the blood pressure and say with the history of hypertension or whatever and say hypertensive, not hypertensive. They will have combined the result of systolic and diastolic. Anybody that have above, once you just have any of them, you are hypertensive. They now use that one. But doing that, you lose a lot of meaning, to be sincere with you. So if you use maneuver, it will give you more, because you capture it in a natural way. Because that's like what I told you. Somebody will measure blood pressure, somebody will have 140, says hypertensive. Another one have 135, it's not hypertensive. Maybe 138, it's not hypertensive. So you can really see the difference. What's the difference? Just like the blood sugar. Somebody 128 is diabetic. 126 is diabetic. 125 is not diabetic. So now, so you see that without the cutoff, though the cutoff is good to make clinical decision, but sometimes also when you are really looking at factors, it is better you use the numerical form to do it, for you to get a lot of hidden information. So we can predict any data using the following general formula or equation. Outcome, we've already said it that we are predicting outcome from predictor. So outcome, it will be you build a model, then plus an error. I usually use some example, though it's just jokingly. I usually use the example. It's not to criticize or to slide something, but I think it's a sensible example I usually use. It's a social example. Anyway, many times when a person want to build a cathedral, what they do is to go and build a model. No, they would not build that thing. That cathedral or that big something. No, they design it. The computer design actually fine. When they design it, now show it after service of Sunday. They first of all play it on the computer to see this is where we are going, our permanent site. So by the time people see the model, people are shy. They begin to donate money. So they begin to donate money. So if they want people to donate more money, it's a matter of trying to play that in so that people to encourage them to donate. So that is a model. The model is not actually the real thing, but it's representing that particular thing, right? So for you to understand what I'm saying better, statistics we study, their real life situation we study, but we try to build model to represent the life situation. For example, equation we write is a model. We say this is regression equation, this height. But it's not height physically you are seeing there, or the weight of physically, but you are representing an equation. Or you draw a graph. Can't you see that the weight of the children are going up? Can you see? But can you see the weight physically there? No, it's a model. The graph, the equation, many things you just to create a picture to represent that. Or you draw a table also, can model. So when we talk about model here, we are just talking about what now try to represent that particular. So you build a model of a relationship between that outcome and the exposure. This is the outcome you want to predict. Then the exposure is not the exposure that is there, but it's a model of the relationship. How the exposure, which is the predictor, and it can be 1, it can be 2, it can be 3. How are they related to this? That is what the model. But the error is when you build the different, because the model may not exactly predict. Maybe some error. So it's just like the example I give about church. After they have donated money to build something, by the time they finish building, people could now discover that what they show in the computer is different from what they build. Somehow that vision, because the computer look more flamboyant, everything. They see the grass there, as the way it look as if it's heaven. But by the time they finish the cathedral, it's not as fine as what they see in the model. So there's a difference between the real and the model. So the difference is the error. Now, the simplest description of a relationship between two continuous variables. And let me tell you something. You see that we are discussing linear regression. This is how you predict a continuous variable. Examiner, when a variable is not continuous now, you see that there are modification. That's where you begin to see something like logistic regression, all those things coming on. for categorical. But now, this the development of origin of regression has to do with continuous variable. We're talking of height of children. It's a continuous variable. So now, the simplest way to understand a relationship between continuous variable is to a straight line. That is how they borrow from mathematics. So we're going to look at in equation of a straight line. You remember equation of a straight line? Okay, before I look at, you remember? Let me just show the graph. Equation, though, okay, well, I didn't even, maybe I would have even put it, but this is regression equation, but this is the way equation of a straight line look like. In the equation of a straight line, y is equal to c plus mx. That a is c. That a you are seeing here is c. A is c. The b is m, the slope in the equation of a straight line. So how they borrow from equation of a straight line is defined by intercept, where the line crosses the y-axis, and slope, the gradient. The intercept is the value of y when x is 0, and the slope is the amount of increase in y for each unit in x. Just give me 1 minute. Okay, sorry, I'm back. Hello. Yes, as I was saying before, I just want to let me quickly illustrate that the equation of a straight line, then the intercept, and let's just illustrate what you see. You can have, okay, I wanted to draw, okay, just wait. Let me redraw it. Let me redo it. Okay, it's in the okay, we have, okay, let me just, this is x, this is y. I want to draw this is x. I want to draw four different y rather, y x. We're going to see different graph now. This is one graph. This another graph. This is one graph. So you can see the difference in these four graphs. Now, in this graph, the slope is positive, that is, it goes up. These two graphs, the one up, the slopes are positive. Then you see this one, the slope is positive. What of the intercept? Where does the intercept slope now, which is the m, let's say slope is positive. Slope is positive here also. But here, the slope for the both of them are negative. Slope is negative because of the way it goes down. What's happening? Negative. Now, the intercept is where the graph crosses y-axis. You know, if you look at this is 0, this is origin, this place is the origin. So for this side, from here to this side, it's positive for x, this side is negative for x. This one above, positive for y, down is negative for y. So here, where does the graph cross y-axis? At the positive side. So the intercept here is positive. Intercept. Let me just write here, inter. Here, look at the intercept. Where did the graph cross y-axis? Is at the negative side. The intercept is negative. What is drawing on this? Now, here, the intercept here is positive because, can you see? Intercept is positive. But, I don't know why it is just intercept here is negative because it's down, it crosses. So you can see, explaining what two things explain straight line, the slope and the intercept. The slope is the amount of change in the y, because when you are plotting in equation of straight line like this, the vertical is the y, which is the outcome variable. The x is the predictor, exposure variable. So y is the dependent, the x is independent. This is the way equation of a straight line is in mathematics. So the slope tell you, look at it, increase in, as this x increase, that is, if the x move from here to here. So if you trace it up like that, about how much does the y increase? It moves from here to here. And you can trace to this place like this. And you see, so slope is the increase in x, then increase in y per increase over increase in x. That is this is what we call dy. You know, if you remember furtherman, dy, this one is dx. That is change in y over changes. So the slope, which is m, in mathematics, usually is slope m, is equal to dy dx. Slope is increase in y over increase change in y per unit change. That is, if there's one change, if the unit of change is 1, how much of change in y? That is the slope. If it's much, it will be slippery. It will be sloping. If not, slope it might be something like this. But if the slope is not much, it will almost be flat. So the second thing, apart from the slope, is the intercept. The intercept is when that graph cross y. And whenever the graph cross y, what will happen? What will happen? Where it crosses, if you trace it to x axis, that the value of x could be 0. That is the value of y when x is 0. We're going to see the logic behind that, because when you apply the same thing to regression, you know that even though when you say you are predicting y from x, it may not be only x, that x you have chosen, if it's only one variable, even if there are two. It may not be only one that determines the value of y. So sometimes, even when that x is not there, y still has value. It means that it's not everything about y, it's not about x. That is not only x that determines y. Because even when x is 0, y has value. And that's why you talk about the value of y when x is equal to 0. And that is where the graph cross y axis. So those two characteristics define a straight line. While the slope talk about the shape, because it's the slope that talk about the shape of the graph, which I told you, if it's very slopey, or either it's positive slope or negative slope, or the slope is much or not, that's the shape of the graph. But the intercept talk about the location in geometric space. You know, the intercept here now is above 0 here, but below 0, that is below 0. The intercept here is positive for y, is below 0, negative for here, when the intercept is down, where it crosses y, not here, sorry, all this on this side, where the intercept are negative. In these two now, the intercept are positive. These two, the intercept are negative. But these two up, the slope are positive. These two down, the slope are negative. Is there any explanation concerning the equation of a straight line? So because you need to understand this to not see how they now borrow it and now use it for regression. Any clarification? Any question? Any question? No question, right? Okay.
Let's move on.
Okay.
It's clear, sir.
Okay, that's
Clear.
great. That's great. Now, so we have already said the intercept is the value of y when x is 0, and the slope is the amount of increase for each unit increase x. So the graphical, in the same graph I just showed better. If you look at it now, in the equation of a straight line, the equation is y is equal to c plus mx, because c, the intercept is represented as c in mathematics, the slope as m. But in statistics, just to change it, you know, when you borrow something, you give it another name. So the intercept is a here. We call it constant. So why they call it c there is because it's constant. Because they call it constant in mathematics. Constant means that even if you didn't bring any, if the x does not exist, that one is constant for y. That is, the value is there. That the value of x of y when x is equal to 0. You know, y is the outcome variable, the dependent variable, x is the independent variable. And the slope is b instead of m. That is what we call regression coefficient. If the dependent variable increased by 1 unit, by how much will the independent variable? Sorry, if the independent variable, which is x, increased by 1 unit, by how much is the dependent variable, which is y, will increase? That is the slope. Now, so the slope is regression coefficient. Constant is the value of y, dependent variable, when x independent variable is 0. So look at the equation in regression. Now this is the way it is written. It's the same thing. Look at the y is equal to BO. Everything, even the constant, it is called, they call it, is a form of coefficient, regression coefficient, B0. That is the constant. Instead of writing A, is in many equations or many statistical package, you see it as B0. That is the constant. Then B1, X1 means the variable, the first predictor, the first independent variable, which is X is the variable and B, X is the value of the variable, P is the regression coefficient. That is that variable, by how much does it increase? By how much does Y increase? Sorry, by unit increase in X. That is the B, Y. So if we now have more than one, this one we extend, I extend the equation, I extend and put plus B2 X2. That is, if there are 3, it can be increasing like that. There are many, depending. So the first one now, just only one, that would be simple regression. If it is multiple, if there are 2, it will be B1 and B2. If there are 3, that's how it increases at so many. So whichever way, the error will be there. The error will be there. That error is just one, because how much are they able to? But in most of the cases, as many factors that are responsible are being fed into the equation, the error will be reducing. To be reducing the error, but it may not completely remove the error. There are as many factors that contribute significantly to the outcome variable are included in the equation. The errors you now get will reduce. Now, how do we get this line? Because is the line equation, that line, when you say the equation, how do we get this line? There are 2 methods. Theoretically, there are 2 methods. You can do it manually. Imagine, look at the next, okay. Okay, I didn't put, okay, I usually put, I didn't do, okay, there's, imagine this line was not there. Imagine this line was not there. You just see something like scattergram. Okay, like the one I think in the, okay. There's one, okay. I think the one is with, okay, let me just pick it out. It's in that regression, that's where correlation, the correlation slide that I put the example here. Yes. Like for this one now, you're seeing here. Imagine you have this line. If I'm to ask you to draw the best line, If I give this thing to everybody now to use hand manually to draw all of them are, if let's say they're on a straight line now, you can easily draw the line that would capture all of them, but they are not on a straight line. So if I give to every one of us to draw it with hand, you cannot draw the same thing. You cannot put the line the same. The line cannot be the same. So different people will give you different this thing because you are trying to, if you want to be close to as many as possible, but you cannot get all of them. You just have to draw one to where you feel is the middle. And where everybody feels the middle will differ. Now, that is manual method for you. So it has its own drawback. So the best method to get the best line is what we call method of least square. Though that line, that best fit is called lines of best fit. The line of best fit is the line that you draw that give the least, if you now have the least distance from the line from each point. That is, if you draw a line, you now calculate each of the point, you now see the difference. Some of them may be on the line. The ones that are not on the line, what is the difference between them? If you are looking at now, all those ones are below the line, they are negative, the distance is negative. While these ones are on the line, the distance is positive. So when you square it, you square that distance. There's one thing with intelligent people. They always think intelligently and not to violate mathematical rule. You know that when you draw this type of line, you know that those ones are below the line, the distance is negative. The one that are above the line is positive. If you try to add them together, it gives you 0. That is the best line. Because as much distance above that are below. But the intelligent people, the way to work against that, circumvent that, is to square. When you square it, you eliminate the negative. So the line of best fit will be the method of least square. That is the line of least square. What it means is that when you now see the difference from each of the points from the line, when you square it, when you add it together, it gives you the smallest value. That is, if I give to every one of you to draw a line now, if you draw it, we will now calculate each person will probably draw different thing. Now, if we now calculate the distance of each point from each person's line and now square it, the best of the line among you will be the one that has the smallest value. That shows that that's the one that is closest. That is that to maximize the distance, minimize the distance from each of the point to the line. So that line of best fit is the one you get through the method of least square. I don't know if it's very clear. So I want you to ask questions before we proceed concerning what I just discussed. Any question? Or is straightforward? We continue. Is it straightforward?
Dr. Dolapo.
Yes, sir.
Well done. Yeah, I think it's easy to follow. The issue is that there are sometimes when you find points that are lying directly on the lines, how do you take care of those interests?
Well, it doesn't really matter. Even they are lying directly, if you look at this one that are lying on it now, one is on the upper, one on the lower, no matter how small, there's a distance. And if the distance is 0, it's 0, no problem. It's just like when you are trying to, when we draw our Z, you try to draw your normal distribution, standard normal distribution. Some value have the same value as the mean. So their standard deviation is 0. That should be they are the mean true of the graph. So you get it now. So it means that it's on the distance is 0. Does it make sense?
Yeah.
Any other one? Okay, we proceed, right? Now, after you have drawn this line, so the best line is the line of best, the line of best fit is gotten through method of least square. After you have now drawn the line now, that would be your regression line. Of course, that regression line we have is slope, we have its intercept. From the slope, you calculate the slope, that would be your regression coefficient. That would be the value of y when per unit increase change in the value of x. And your intercept will be the value of y when x 0. And well, there's something maybe before I come back to now look at, because what I just said now, yes, there's something for you to see. Got a lot of, okay. The B you see, this is an example. But this is an example. I will still come back to those ones. This is an example. This is the example we used yesterday. It's the same example we used yesterday. The height and pulmonary death space. You see, it's the same graph I showed here. This same graph. But try to put the X there and put the line to draw the line, the best line for it. And when you finish doing it, the B, we already said that the B is the change in Y per unit change in X, right? How do we achieve it? No, yesterday we talked about covariance, how Y and X vary together. So we have come up that covariance, you remember the formula for covariance, sigma x minus bar x into y minus bar y over n minus 1. That's how we calculate covariance. But when I say correlation is a standardized covariance, when we divide the same thing by the standard deviation of the two of them, of x and y, it gives us the correlation, correlation coefficient. Now, look at this. You will see if I pick, it's good because this is a workshop, even though it's a virtual one, it's good. Sometimes, as you are presenting and you remember something, so that make it easier for people to conceptualize. This one correlation, I want to pick something from that correlation. Yeah, that's it. For us to understand. Yes. Look at the covariance. So for the variety like Dr. Larry was on here yesterday, the covariance is this one, covariance. Sigma x minus s bar y minus y over n minus 1. This covariance. And when we divided this covariance by the standard deviation of both of x and y, it gives us the correlation. Can you see the formula for correlation? Sigma x minus s bar over y minus y bar over square, which is the standard deviation, square root of sigma x minus s bar square. If you remember. So what cancel out here now? Because the n minus 1, n minus 1 from both sides cancel out. So now what I want you to see here, the regression O is the, can you see? Okay. The difference between correlation and the regression equation. I want to see the difference between correlation and regression equation. This is correlation. I'm bringing it. Yeah. You see correlation? This first one is correlation. You see correlation? Can you see the formula for it? Look at the denominator. Look at numerator and denominator. Look at regression. You see the numerator is the same. Here, what is not is here is that is not the square, is the variance. If you look at the sum of, you are not finding the square root here and variance of x. So, you know, covariance, the upper part now is the covariance, how x and y vary, divided by the variance of y. So, of x rather. So, it will, that was now give you the change in y per unit change in x. So, this b, can you see? So, this b is actually the change in y per unit change in x. So, change in y that is due to change in x must be a change that's change between y and x together. It is when y and x, what makes them covary. That's change in y that happen. So, it's the covariance of both of them divided by the change in x, the variance of x. I don't know if you get the logic. Now, the funny way, if you use and because we're going to call it, if we are going to look at it now, if you use and to calculate, maybe just do it before I go to explain. Let's just look at it now. Let's just look at it together. Look at the data set. No, we have already, why I didn't put the thing here was that we have already computed everything under the, what do I call it? Under the correlation. We have already computed everything in correlation. How the results, okay, where is the Pearson correlation? Yes. We computed it. Okay, yes. We will compute it under the correlation. Yes, let me just finish. Let me put here. So, I thought I put, no. Just a minute. I want to drag that. I want to bring that comfort. Yes, this is what I wanted to do. Yes, I want to see it. So, if you look at it, we have computed all these parameters, x minus, look at s bar minus the covariance s minus s bar, y minus y bar. The summation is here. Then x minus s bar square without the square root is here. Can you see? Is this value. So when you now go and look at the formula for, can you see? If you put it here, look at it. 5426.6 divided by 52516. That is it. This correlation coefficient. And once you calculate that B from that, A constant is just for you to say A, if you remember the equation of the straight line, let me annotate. If you remember the equation of a straight line, y is equal to A, or you can say y is equal to A plus bx. So if you shift, remove, or you can say A plus b is equal to y. If you want to change, make A the subject of y, which is the constant, which is the regression, we are already the value of y when x is equal to 0. It's going to be y minus bx. So from there now, you have already known x, you know x, when you calculate the mean, we have calculated the mean. If you look mean x, mean y, you feed in this one, it gives you the constant. So the regression equation will become like this. So if you have somebody now, all you need to know is to know their x. If you know their x, you can predict the y. Then whatever remains will be the error. If you know x, if you calculate, somebody just gave you, let's say now, the height of the child. I want to calculate the pulmonary dead space. If you go back now in this data set now, yes, we choose one in this data set now. We can decide to choose a value 44, no 110. That's x, the height of the child, and now put in an equation. It will not in that equation. It will not exactly give you 44. The difference is the error. It will not exactly give you that 44, but the difference will be the error. I don't know if you have a question concerning that. Do you have a question concerning that? Any question? Okay. If there's no question, then let's now go back before we go and run it. Now, I want to explain something. After you have filled, you have produced the line. That thing I've gone to now is the slope b, and know how we calculate the slope and the constant. That's what we just simply want to do for this graph. But before you can rely on whatever slope and the constant, because the slope is the regression coefficient, what you are looking for, and the constant is value of y when s is equal to 0. Now, before you go and rely on whatever it gives you, you want to test the goodness of fit, assessing the goodness of fit of that regression line. How are you sure that this line is fitted very well? Yes, I mean, before you just accept that the value of b and a give you, how are you sure it fits very well? How do you assess it? So the assessment of goodness of fit here is different from the chi-square for assessing the goodness of fit. So that one is a different thing. This one is assessing the goodness of fit of the regression line. This is where you go to know the ANOVA and regression is the same. Because ANOVA is one of the things you use to assess the goodness of fit. And the correlation also asks something to play, a role to play here. So method of assessing the goodness of fit, there are two of them. The R square and the F ratio. The R square is the proportion of improvement due to the model over the improvement due to the, okay, that is why I arranged that graph like that. I want you to, before we talk about that much, let's look at the graphical representation or the variance. So let's study this guy very well. When you understand this guy, a lot of things will unfold. Now, look at this first graph. What this first graph is showing us, if you look at it, it's not showing, it's showing us, look at the same graph of y. The graph I just showed now is the one of this side here. This graph is what you have here. Now, this graph is the same y and x, but this one, though it's the same graph, anyway, it's the same graph. This graph is still the same graph, but it's the line we just draw through that differ. Sorry. Now, this line go through the mean. This one, the mean of y. The crudest model, if you remember, I told you in the following, I said the crudest, the most basic model is the mean. The mean in the deviation is observed sum of observed minus model square. You know, if you remember, I told you that mean is the crudest model because mean is what we call expected value. And what is expected value is the value of y. Is the value when non-hypothesis is true. If somebody want to maybe want to buy something for children now, no, I usually give an example and say, oh, you have a nursery school, and maybe your friend went to UK, so let me buy some jersey for Intersport for our children, sport wear, and one high quality thing from UK, let me buy. The question your friend may ask, oh, I'm going there now, I'm there now. They ask you, what is the average age of your student? Oh, you now quickly call the head teacher. Say, what is the average age of our student? Now say, oh, the average age is 7 years. So, either you like it or not, there will be an assumption that they are buying things for 7 years. They go and jam pack cloth for 7 years. You can bring 150 cloths, for 7 years people. Whereas that 7 year is just the average. Some are less than 7, some are more than 7. So average is a crude model. It's believed that all of us, how do you get average? They add all the ages together and now divide by the number. Now share the age equally among everybody. If there are 150 students, they now had all their age together and divide by 150, and that's 7 years. They are assuming that all the 150 students are 7 years. Whereas some are less, some are more than that. So that is why average mean assume that everybody is equal. That is an expected value when there's no difference among the age of everybody. In the age of all the students, the expected value, that is the mean. I usually give an example also. Maybe 5 of you did one something, they give you 100,000. You say, how do you share it? So you say 2020. But there's an assumption that all of you are equal. If Professor Wakwe is there, is the leader, you think he may not allow you to take do like that. Wakwe can take 50,000 from the 100,000 and I say go and share the rest because it's the head that's there. So you have assumed by saying 2020, you assume that all animals are equal. But all animals are equal, but some are more equal than the other. So that is how mean assume that everybody is the same. It's the crudest model. Now, how do you apply this principle here now? So there's no better way of assessing the goodness of regression line except you now compare with the crudest available. Without even using and doing any regression, you can easily calculate the mean or y you are predicting. You have the model, which is the crudest model, as the mean. And that is why this line, horizontal line, is the mean line. Just draw like that. You can see some are above, some are below. But you can see that it's the crudest because if you look at it, the distance from each point, average distance from each point to the mean is wider than the one you see in the regression line. This second one is the regression line. Can you see? You will see the regression is the same data you draw the regression line. Here you draw the mean. You draw the regression line. You discover that the regression line, the values are closer to the line than the mean averagely. So the mean is the crudest. So you are using the crudest, the most basic model that's available. You are trying to compare with your regression line to assess how fit that regression. How do you do that? You want to say, okay, now we know that this mean is very crude. What improvement has this model made? What made this model better than me? If it's not too much better than the mean, that should that it's not. But if it's far better than the mean, that should that is very fit. I don't know if you get it now. So that is why you now come to this third graph. Now overlap the two. When you overlap the graph for the mean and the graph for the regression line, The difference is the improvement. So now, if you remember those of what that were in ANOVA class, this is where the knowledge you got from ANOVA will be very useful in regression. If you remember, we said there are 3 levels of variation in the data set in ANOVA. We have the total variation, total variance, which you got by removing each value from the mean and square it. Are we together, please? If you look at this first one, the mean is the one that shows you the total variation, because the mean is the horizontal line. The distance between each point and the mean is the difference between each one. Though some are negative, some are positive. The one below the mean are negative, the above they are positive. When you square it, that will be the sum of square total, SST. Sum of square total. And it's the same thing in ANOVA. When you remove each value from the grand mean, you remember in ANOVA, we got our grand mean 2 ways. You can add all the data set. You know, ANOVA, maybe like example we use in our ANOVA class, we use example of 15 people and 555 placebo, low dose, high dose libido, and we now each class has its own mean. The grand mean is gotten by adding all the 15 together and divide by 15, it gives you the grand mean. Or you can add the 3 means of each class together and divide by 3, it gives you the same thing. That is the distance from each value and the grand mean, and that is counterpart of what. So you give us the sum of square total, and that is what you have here. Sum of, if you the distance between this mean and each point, you square it, it gives you sum of square total. Sum of square total using the difference between the observed data and the mean value of y. Now, when you come here, if you remember in ANOVA, we talk about mean, the variance within each group. When you remove each value in each group from the mean of that group, or mean of each group from each value, the difference between them, and square it, that is variance within. This is what corresponds to this one. This is what called residual. Here, when you are draw your line, regression line, the difference between each point and the regression line is the error. You know, the regression line is the model you are built. Now, the now happen that not all of them fall along the line. So the difference of the line from between the line and each value is the error. That is the error the line has in predicting each value. So if you square it, some are negative, some are positive. The ones that are below the line are negative, some are below the line are positive. When you square it, that will be sum of square residual. It's the one that corresponds with the sum of square within group in ANOVA. You can call it sum of square residual or error, but residual. Now, you can now see that if you remember in ANOVA, we said that the sum of square within, if you remove it from the total sum of square, it gives us the sum of square between, which is the model. So here, when you now overlap this graph, you will now see that you are looking, okay, this one I just explained, I say sum of square residual, you see the difference between the observed data and the regression line. When you now come here, we overlap the two. The sum of square model, which is the one that corresponds with the sum of square variance between the groups in regression, is using the differences between the mean value of y and the regression line. Can you see? the difference between the mean and regression line. When you overlap, in between, this is the mean line, this is regression. In between. So the difference now, that is the improvement. That is the improvement the regression line has made, which is the sum of square model. The only thing there is that in ANOVA, you can actually calculate out with hand the sum of square within, between, total. But if you add within and between together, it gives you the total. Or if you remove within from total, it gives you between. Or if you remove between from total, it gives you within. But here, you can easily calculate for the total and for the residual. And now remove, when you remove residual from the total, it gives you the model. And that is the way to the regression. I don't know if there's any problem understanding this. Is there any problem before we proceed? Any question in understanding this graph and how you can relate it to how is the same thing with ANOVA? And that's why by the time you run regression, you go to see ANOVA there. Are we together? So it's very clear. Any question?
Very understandable.
Oh, that's great. Okay, now let's proceed. Now, the method of assessing the goodness of fit, I come back. R square and F ratio. The F ratio should not be new to you because in ANOVA, we talk about the F ratio. That's the same F statistics in ANOVA. Yes, and you remember that F ratio is comparing sum of square between divided by sum of square within. That is trying to compare how much variance between is more than variance within. Because the variance between, which is sum of correspond with sum of square model here, is the improvement the regression line, your model has made. That is your model. Improvement that regression line has made. So when you now want to know how good that improvement is, now divide the improvement by the error within. The error it has made also. It cannot get everything. It has error. It has made improvement. Just like somebody, you get some question right, you get some question wrong. You will pass if the question you get right offset the one you get wrong.
Once you got wrong.
Yes. If the good you have done, if it offsets the mistake you have made, is better.
Okay.
Yes. So here, the model is the improvement you have made. You want to divide it, you put it as numerator, divided by the error. The same way in ANOVA, you put the sum of square between, which is the model, over the within, which is the error within, the variability within. So if you look at it, both of them are the sum of square, they are variance. Remember from what we just described in this graph. Because if variance is a x minus x bar square. You know what we just did there? We were trying to look at variation. Yeah. That is the difference between, that is the deviation. Each deviation, you square it. That is it now. Sum of square total, sum of square residual, sum of them model. So now, F ratio is sum of square model divided by sum of square residual. Now, the R square is the one, by the time we run it now, you get it clearer. Got to explain something, get it clearer. R square is, as the name implies, there are two ways to get it. By the time we run it, this R you are seeing is the correlation coefficient. You square it, yes, you square it. Correlation coefficient. So I think, don't worry, I will not talk much. Just know that R square and F ratio, those are two to fit together. When let's run it, I will now, yes, measure of goodness of fit for regression line. So when we run it now, we're going to run it now. We're going to see, I will now explain the R square further there. But I don't want to talk, bite my tongue. I will explain it there. And both of them also, and this one, you're going to see clearly. So, any question before we go around it so that we'll explain further? Any question? Okay, either the case, somebody should share that particular, let's just use that particular, somebody send a message. Good evening, sir. Like, can I join the next week? If I ask questions and this is not clear to me, and oh, you are free now. Wait, look at this. Oh my God. So you are free. Which one is not clear there? Okay. Which one is not clear? Ask your question, please. Ask your question. Please ask your question. Ugo, ask your question now, or is not there?
No, I understand it now. I understand it. Thank you.
Oh, but you said something that you were not following, that you didn't understand.
It was towards the end.
Towards the end, you didn't know which
Towards the end, I got it.
Which one?
And I watched the video.
No, ask it now. Let me, which part of the end? So that I just quickly repeat it.
No. Hello?
Yes, go on. Go on.
Doduro?
Yes,
just to confirm.
Okay.
Okay, just to verify, the model is that final one we got, while the error is the one that had the regression, like with the different.
Exactly.
You know that's the okay.
Look at it.
Okay.
Look at it. This is the error. This is the model.
Okay.
And it's by removing you are removing error from the mean. You know, the mean is the total variance that can be explained. You understand me now? Okay. Total variance. If you look at it, if you look at they are very far from the line. You understand me now? The individual value are far, averagely, they are far from the line. So, and this error, this one, they are close, but the model was able to get closer, but it still have error. It has not captured everything. I don't know if you understand me now.
Yes.
Now.
Yes, I do.
So the total variability to be explained is just like this one present the total problem. I mean the mean. This one, the total. Why this one?
Yes.
Explain the problem that has not been solved. This is the total problem. This is the problem that has not been solved. That shows that for you to know the problem that has been solved, remove the total problem, the problem that has not been solved from the total problem, you know the one that has been solved. You understand me now? Okay. And that is what the model show you. So, and this model is the one that corresponds sum or square between group in ANOVA. This error is the one that corresponds with sum or square within.
Okay, in ANOVA.
Then this total sum of square here is the total sum of square in ANOVA, the one that relates to the mean, the total sum of square in ANOVA. Does it make sense?
Okay. Thank you, sir.
Okay,
yes, sir.
Yes, somebody should share yesterday's what we used yesterday. That same pulmonary dead space and height. Quickly share and let's run it. You're going to see this thing clearly. Who is doing that? Who is sharing? Dr. Bako, can you share? Dr. Bako? Hello?
Hello, sir.
Can you share?
What will I share, sir?
The height and pulmonary dead space.
What will I share, sir?
Height and pulmonary dead space, the one we did yesterday for correlation. Height and pulmonary dead space. There's a data set.
What will I share?
You cannot hear me. height and pulmonary
space.
Yes, and pulmonary dead space.
Yes, let me open it.
Okay.
No, I'm opening it. Okay.
Okay.
Dead space.
Yes.
I'm opening it.
Okay.
Okay. Height space. Yes, let me open it.
Okay.
I'm opening it. I'm opening it.
Okay.
No, it's coming up. Slow. Yo, look at that. You have to enable me to share, sir.
Okay, okay, sorry. Okay, I've enabled. You can share now.
All right. Are we there, sir?
It's coming up.
No.
It's coming up.
All right.
And your computer used to share fast. What happened? Have you introduced virus in your computer or what?
I am.
Okay, where you are, there's no network.
Not as strong as in my.
Okay, okay.
Yes, the network is
I
not.
know that it doesn't take time.
But I've shared.
No, it's sharing. It's
No.
sharing.
Yes.
It does not come, but it's sharing. Why is it taking so long? Okay, who else? Or maybe I should do my own.
Yes. Yes, because it's just wasting time.
Maybe I should. Oh, the other people don't want. Jane, you don't want to share your own. Ugo, you don't want to share your own. Huh?
Okay, I'm using my phone, but I can connect with my laptop to share.
Okay.
Hello.
Because most of the time,
if that will not take time, you just give me a minute and I'll connect with my laptop.
You can connect, but Ugo, you can share your own. Okay. I think where.
No, my own is that it's even raining on my end now, so the network is very, very bad.
Raining. Okay.
Okay, let me connect with my laptop. Let me connect with my laptop. I think.
Okay. Because it's not that I cannot do it yet. But I just want you to be part of it to make it. You learn better.
Ima, if you are there and your SPSS is up, why not start sharing? Why I try to log in with my laptop?
But does he have? Did you send this something to him? Does he have the data set?
Ima, was it not the one that down? Okay, I didn't share the data set with him.
Hello, ma. I have not received the data set yet, ma.
Yes, you will have.
Okay,
I will share. I will have forwarded it to you yesterday. Okay, yeah, Dr. Bakwas shared it. So this is the data set. No, we used yesterday, yes. So I want us to first of all do the correlation we did yesterday first before you go and do the regression. So go to analyze. Go to correlate. By various, yes. So move the two of them. Move the two height and pulmonary dead space. Yeah, just click OK. No, don't check those on. I don't need those sperma and candle. Remove them. It's only the spacing, yes. Just want you to see. Okay, share the result. Let people see. Share the result.
Yes.
You in the man. Okay, but I can see. Wait, don't worry. Since I can see, everybody can see.
It's actually shared.
Yes, it's shared because everybody. Once I can see, just leave it. That's gone. If you remember, look at the correlation is 0.846. Please note the correlation. The correlation between height and pulmonary dead space is 0.846. I just you should note. Okay, now go to analyze now. We have noted the correlation. Go to analyze. Just go to analyze here, yes. Now go to regression. Regression.
Yeah.
Regression.
Yes. Yes.
Linear. Click on linear. Go to linear. Linear regression. Linear. Yes. Yes. Now move. The pulmonary dead space is the dependent. Yes. Pulmonary dead space is the dependent. Yes. Then height is independent. So now click OK. Click OK. Yes, that's great. Yeah. So don't scroll down too much. Let's see from the beginning of the table. The first table is up. Let's start looking at it. So it's okay, it's okay, it's okay.
This regression.
Yes. So I want you to look at these tables. Just wait. I want to bring the annotation. I don't know why. Okay. Look at these tables. You will see something is making no noise. Okay, so I'm gonna have stopped it. Okay, now look at what we have here. No, somebody's okay, it's Jane. Please off your this thing, it's echoing my voice. Yes. Now you see the first table talk about model. He put height in meter inside the model. Can you see? If you remember the equation, I say the equation y or outcome is model plus error. The model is the one that talk about relationship between the x and the y. So the y is outside. The dependent variable is pulmonary dead space is outside here, but inside the model is the height. If let's say by the time we do multiple regression now. Oh, Dr. Koba, I thought you say you were going out. You are in the theater. I can see you in the theater. So well done, sir.
About entering theater.
Sir?
I'm about entering theater.
Yes, I can see because I can see you, sir. Yes. Don't worry, just as many you can catch, you can join us next week also, no problem. So you will see that the model, inside the model is only height that is there because it's only one independent variable we have. By the time we do multiple now, we had another one. We're going to see another one there inside the number of variables you feed in as the independent variable that will be there inside the model. Whereas the outcome variable will be the one outside. Now, that is that. The next table, summary, model summary.
Okay, sorry, sir. Sorry, sir. Before you move to the next table, go back again and explain this table, the variable entered. This one where you're saying you're talking about the model. What the model and what is outside the model? Please explain that again.
What is outside the model, outside that you look at it now. You see dependent variable. Pulmonary dead space, that's the dependent outcome variable. But in regression, the outcome variable is only one. Almost only one. Always only one. But the independent variable can be one, can be two, can be three. But here now, it's only one independent variable we have, which is the height in meter. And that is the only one that constitutes the model. And that is why it's a one. That's the only one, height in meter. It's a variable entered, height in meter. So I think that's clear now. Move to the next table, model summary. You will see R actually correlation coefficient. The correlation we did, what's the value? Is 0.846. The correlation we just did between them, yes, 0.846.
Yes, 0.846.
That was why I said you should note the value. There's a correlation between the two variables. Then you now have R squared. That is 0.846.
You should square it.
Square it. I think you can try. Please everybody should put your, because part of it, that's how it's mistake. You can have your, what do I call it? Your phone, whatever, use something. 0.846 times 0.846. What's the answer? Please, let's quickly do that. 0.846 multiplied by 0.846.
Okay, that is 0.7. 0.715.
15 something.
Olga says 0.72 approximately.
0.716.
716. If you look at the R square, can you see that? Yeah, you can call it 72 or 716. Look at it. Look at the R square here. 0.716. So it's the square of this correlation. So another way to get it, please come back here. Put this, go to the ANOVA table, the next one. You will see sum of square. Put that sum of square, the one regression, which is, yeah, it's okay, which is 5607.432 divided by the total. Please, somebody should do it also. This 5607.432 divided by 7828.933. We are dividing the sum of square regression by the total sum of square. Hope somebody, that's why the young one should do it, so that.
Okay, divided by what?
By the total sum of square, which is 7828.933.
0.716.
Can you see it's the same thing? Can you see? When you square the correlation, it gives you 0.716. When you divide sum of square regression by the total sum of square, it gives you 0.716. It's the same thing. So that is what they call, when you express this as percentage, it is called coefficient of determination. The coefficient of determination is the percentage variation in the outcome variable that is accounted for by variation in the exposure variable. That is the percentage variation in Y that is accounted for by the percentage variation in percentage variation in Y that is accounted for by variation in X. Does it make sense?
Yeah.
Yeah.
So what it means is that 0.716 means 71.6% of the pulmonary dead space is due to height of the child. Does it make sense? So if the height of the child contributes 71.6% of the pulmonary dead space. So that shows that it's not the height alone that account for the pulmonary dead space.
Pulmonary dead space.
But it contributes up to 71.6. That shows that it's a major contributor. Because there's no other factor that can contribute that. Because you can now have more than 100%. So if one factor contributes 71.6%, that is a major factor. In fact, any factor that contributes more than half is a major. That shows that even the remaining percent will not be contributed by only another one factor. It may be several factors. So it is clear here that that particular height is contributing a lot. But however, if you do multiple, by the time we get some other factor around, we may see the effect. If it's possible there is a related factor that contributes that much, it may be, maybe that factor is not around, is confound, this one is confounded for this. But if these are the factors that are related, this is the major factor that are related, is the major contributor. That is why regression is very important. I told you of a situation where somebody, you did a study, many factors jump together, it's not even up to 20%. What is telling you that all those your factors you have put, if they are not up to 20%, that shows that there are more than 70 or close to around 80% of the problem that is accounted for by some other factors, which you have not captured in your study. So giving recommendation on factor that does not even contribute up to 20% is a waste. So if you understand research and statistics very well, you don't even waste your money on that type of recommendation. And that's why, if you understand statistics very well, you will not conclude, you don't even read anybody's conclusion. Rather read the methodology and read the result. When you read the result, you can make conclusion by yourself. That was why the Israelis said that there are 3 kinds of lies: lies, damn lies, and statistics. People can tell lie with statistics. Now, I think you understand coefficient of determination now.
Yeah.
Yeah. Let's proceed. Now.
Okay, so sir.
Yes. Go on.
Okay. So when I run this regression now with this my study that I'm working on presently.
Yes.
This might impact something that I'm working on. So by the time I run regression with this now, I'm able to tell the contribution of my intervention.
Yes, yes, you'll be able to. But is your outcome measure? What is your outcome measure? What is your outcome variable?
Okay, I'm looking at the reported cases of malaria.
Okay, reported cases of malaria now is qualitative.
Confirmed, uncomplicated malaria,
yes,
and severe malaria.
You are not going to run later, after.
Hello.
Yes, I'm listening. I heard you.
It's off.
I'm not awful. Is it that my distance
looks off?
Okay.
I'm not off. Or is this thing behaving funny?
Malaria cases, confirmed malaria cases would be my outcome measure.
I heard you. Yes, I heard you. Can you hear me? Yes, I heard you. I think everybody can hear me, right?
Yeah, it's gone off. I think it's the network. Back on.
Okay. Can I ask a simple question? Hello?
It's not on, no. It's not on.
Okay, it has gone off.
Yes.
It was a network problem.
Okay, I'm hearing you. Can you hear me? Can you hear me now?
Yes.
I can hear you now.
Yes, sorry.
Yes, sir.
The thing went off. I didn't know that it muted me. Okay. I heard what you said now. You say malaria cases. I said that before you ask your question, sir, Dr. Kobo. Okay, you can ask your question because since you are doing surgery.
Since I want to let me ask now.
Ask your question.
So
Yes.
From the statistics here, that's what I'm asking. From the statistics here is the R square that is the most important part of the statistics, because that is what you use to make your inference. You convert it to percentage, like in this case, 71.6% of the permanent dead space contributed by the height in meters. Then what is the work of the adjusted R square?
Okay, the adjusted R square is just the same thing. The R square here is statistics. The adjusted R square is parameter. So what is the R square is what you get for your sample. So in the population, this is what you get. This adjusted one is the parameter. So if you look at it, it's a bit lower, but it's still high. So that's how it will be in the population. Yes.
Okay.
So that is the R square. I'm coming back to your question, Jane. That is R square. Remember when I was trying to explain the importance of R, I say I defer that R square to this time because I've explained the F ratio. So that's one of the things, the two things you to fit to know if the model is good. So your F ratio and R square. But to me, the R square is more important than the F ratio. So it is when the R square is good. That's why you say you can base your judgment and now go and look at the regression coefficient and now use it. But if the R square is not big enough, it's a waste. It's a waste of time using that. I don't know. I'm not. Your study is not a waste, but what you have found is not robust. You cannot give me a recommendation. I will not go and do it. If you go and work on that type of recommendation, you are just wasting time. There are people that did study that even their study is not, it does not contribute up to half. The R square is not up to half. When you even combine many things together, it's not up to half. And they are giving you a recommendation. If you go and waste money on that kind of recommendation, it tells me you cannot solve up to half of the problem. That was telling you. So if your this thing is up to this, about 70% that like this, of course, if you carry out recommendation, you are attacking 70% of the problem. Is big enough. You are attacking 70% of the problem. If you can make improvement, there will be drastic improvement. And that is what many people don't know. Now, you can now see now, you have to first of all, okay, use the F ratio and the R square to first of all see, is this model fit? Is it good? Goodness of fit. So that's that. Now, the F ratios also, how do you calculate it here? You know you have calculated the R square. How do you calculate the F ratio here? Or you know, regression, the sum of square. If you look at my internet is coming, because that was what it, can you hear me now? If you remember the regression sum of square regression divided by, look at it too, divided by the degree of freedom, it gives you, can you see? If you divide this, because the degree of freedom is 1, you now divide it, it gives you this, the same thing. The sum of square residual, which corresponds with sum of square between, within, and over. If you look at this, the title of this table is ANOVA. If you remember when we run ANOVA, this is exactly the way the table is. The only difference you see here is that instead of regression in ANOVA, you call it between. Instead of residual, call it within. That's all. Between, within. It's only the nomenclature. Everything is the same. In fact, we are going to use, I will ask somebody to use that, our libido's something data. We run ANOVA and run regression. You will see with it. Because I created the dummy there. You see, you get the same thing. Now, if you divide this one by the degree of freedom, it gives you this. So the mean square regression over the residual will give you 32 points, which is F, and it's significant. Can you see? Now let's now come to the last table. The last table. Okay, before we come to the last table, you see the F ratio and the R square. What are they? R square is telling you what proportion, what is the contribution of that model or that model to the total variability. Yeah, the total variability that can be explained in this data set. How much of it is the model as explained, That's why I put the sum of square model over the sum of square total. No, we have already showed them graphically, the model and the total and the residual. Yes, so that's what it's just telling you. Whereas the F ratio is telling you, it says, okay, how among the variability explained by the model, divided, before you can say it's good enough, you divide it by the one it cannot explain, which is the residual. If it's big enough, it should be greater than 1. Not only greater than 1, should be, look at this, 32.8 times. So what the model can explain is 32.8 times, more than one it cannot explain. That's why, is it not good enough? And that's why it's significant. Now, the last table is the table that now shows the coefficient. Yeah, now we're not talking now.
Okay, so at what level sir?
Go on. We cannot hear you.
Sorry, sir. Before we move on, at what level do we say the model is not good enough? No.
Sorry, sir, you're breaking, sir. Sir, you're breaking. We can't hear you again.
It's you are breaking.
You were breaking. We couldn't hear you again, but you kept on talking.
And me?
We're here. We can hear you now. Sir, can I say something? Hello?
No, it's yes, it's Jane that was asking question. I can hear you.
It's off.
I'm not off. Oh, am I off? I'm not off.
No,
no. Now.
It's the host.
No, I'm hearing. I'm hearing now.
It's the host that is breaking.
You know,
yes.
Let me see. I can hear you.
I think we can't hear you.
I can hear you now. Can't you see my
Okay,
hand?
I was that what percent, like now what we have here is showing 32.8%, which says that the model is able, the model is good enough to be used. So at what level do we say this model is not good enough? What figure? What is the minimum figure we should see here that would, cause us to make us to arrive at the conclusion that the model is not good enough? What's the minimum value of F here that should make us, take the decision that this model is not good enough to give us what we want?
It's off. It's off. Bro, you are off. It's off.
Okay, I think he has connected back.
In